Welcome to the Ask Me Anything review session for midterm 2. Thank you to those of you who submitted questions. I'm going to try to phrase them in a way that makes this as general as possible, and I think there's a lot of really useful stuff in this very short video. So the first question asked about the shape of the DLVO curve. So a DLVO curve has a shape like this, which is energy versus distance of separation. And what we have is a kind of a superposition of a repulsive term due to the electric double layer interaction, which of course is due to the osmotic repulsion of the diffuse double layer of counterions around a charged surface in a liquid medium, usually water, and we have this attractive component due to the van der Waals attraction. Now, I really probably didn't draw this quite right. Probably more like this or something. So typically how one draws this is that the van der Waals force dominates at small distances of separation, and this is called the primary minimum. Then there's a repulsive barrier due to the electric double layer repulsion. Of course, we want this to be as strong as possible to ensure stability of the colloids. We want this to be high enough so that as the particles approach to one another, there's enough of a repulsive barrier to keep them separated. Now, this is a secondary minimum where a stable colloid tends to live. So Ds will tend to live around here. Now, there was a question about the Pauli exclusion principle, and does that still apply in this case? Yes, but that only tells us something that's kind of obvious, that the particles can't simply just merge into each other in a quantum sense and take up all the space. So if you really care about the distinction here, you also have to worry about the fact that at very small distances, and this line is a terrible shape, but of course we know that you can't have the distance increased or decreased down to nothing to where the particles are actually overlapping. I would never ask you in a DLVO curve to put this. If you put it there, it's not wrong. It's certainly correct, but we wouldn't ask you unless you wouldn't be expected to put the contribution due to the Pauli exclusion principle. But if you think about it, if you think about it, there's actually some similarity here between the DLVO curve without the EDL portion and the Leonard-Jones potential, which had this repulsion term at short distances that we saw earlier in the class, where the Leonard-Jones potential was something like that. Okay. The second question had to do with what do I mean by ideal conditions for the oscillatory solvation force? So oscillatory solvation force. What do you need? You need small, I forgot that in this class we write in all capital letters, small solvent molecules. So things that are only maybe a couple atoms, a couple of carbon atoms long, maybe up to like hexane will work. They can't be branched, so they have to be small, symmetric solvent molecules. And two, we have to have flat surfaces. Remember that if we have roughness in the surface and it's about a third of the hard sphere diameter of the molecules, then the oscillatory solvation forces will be greatly reduced. Now we can have relief structures on the surface, but they have to be regular. So regular relief structures are okay. What do I mean by regular relief structures? Well, a regular relief structure could be like this. They don't have to be commensurate. It helps if they are. What else do I want to say about this? Also, if the roughness is compressible, then we have the oscillatory solvation forces that return. Okay, there was another question about interlayer slip versus interfacial slip when talking about the presence of molecular lubricants. This is not something you should worry too much about, but just by way of example, if you have two surfaces like this and you slip, this might be called interlayer slip because it's layers between the solvent, whereas this would be interfacial slip. I didn't talk about this in the lecture, so don't worry about it, but somebody asked, so here it is. The next question had to do with the difference between the Florrie radius and the radius of gyration. Okay, so the Florrie radius is like the real radius of the polymer blob inside a solvent, whereas the radius of gyration is the mathematically determined radius that assumes that there is no intermolecular forces between the polymer segments and between the solvent and the segments. So the Florrie radius, in the literature, we tend to see it all called the radius of gyration. So what's the radius of gyration in a particular solvent? You could also call that the Florrie radius. But the radius of gyration differs from the Florrie radius in that the radius of gyration is a mathematical construct that represents the RMS distance, the root mean squared distance between the center of mass of the polymer and all of the segments within the polymer chain. If we put it in a bad solvent, so a solvent that doesn't have strong interactions with the polymer segments, then the polymer chain will ball up and RF will be less than Rg by a ratio of alpha, which is the intramolecular expansion factor. So if it's in a bad solvent, alpha will be less than 1. If it's in a good solvent, alpha will be greater than 1 and the polymer chain will expand. So in the case where alpha equals 1 and RF equals Rg, we can say that in such a case, that would be in a theta solvent, the interactions of the solvent molecules with the segments in the chain are such that you get the same molecular dimensions of the polymer blob as you would if you had no interactions whatsoever between the solvent and the polymer or the polymer and the polymer. So what that is, so in a theta solvent, another way to think about that is in a theta solvent, what we have is a mathematical construct that has rotating bonds and moving bonds between the segments, but no intermolecular forces. So is that really what's happening in a theta solvent? No, it's just that the effects cancel out. Okay, the next question was about the triple interface and the contact angle. So in a triple interface, we have the liquid, the gas, and the solid. Now, the contact angle is dependent on this energy balance between the gas, liquid, and solid. So we have three different interfaces: solid liquid, liquid gas, which is also known as the surface tension. It's probably the value that we can just look up most readily, because it's just the value of the surface tension or surface free energy of a liquid with vacuum or air. And the gas-solid interface, which experimentally isn't usually that important to, oh no, I shouldn't say that, that's not quite true. The most prominent variable we have to tune here is the interaction between the liquid and the gas, and that's the surface tension. So why would mercury have such a large contact angle? It's because there's a big penalty for a liquid molecule of mercury to go to the surface, because it's so satisfied being in its van der Waals, being in its metallic bonds with its neighbors in the liquid state, and it doesn't want to go to the surface. Now, that doesn't say that if we had a higher energy solid, that we couldn't get the mercury drop to spread out a little bit more. So if we had, say, solid 1 and solid 2, where solid 2 had a higher surface energy than solid 1, you could still get the mercury to spread out even more. Now, if this were Teflon, you might expect the mercury drop to become even more like a sphere, so an even greater contact angle. Okay, the next question deals with critical micelle concentrations. And we have the concentration of monomers and aggregates versus the total concentration, which is the concentration of monomers plus the concentration of monomers involved in aggregates, with aggregate number n. So n for a monomer would be 1, for a dimer would be 2, and so on. So as we increase the number of monomers, we get to a certain point where the number of monomers stops increasing and it remains flat. And at this point, this is called the critical micelle concentration, we start forming micelles, or aggregates, which increase with the rate of increase of monomers that we add say from a bottle into a solution. And this is X sub n. Okay, now down here we have another curve that rises less steeply, and this is the concentration of aggregates, xn over n. Now think of some circumstance. Now critically, all of these concentration values refer to the concentration in the bulk solution. None of the concentrations at the interfaces, so none of the concentrations count, or none of the molecules at the surface of the liquid count. So the liquid air surface, none of the molecules at that surface count toward the concentration. And if we add additional surface like oil droplets or air droplets, air bubbles into the mix, you're going to have monomers flock to those interfaces to lower the surface tension of the liquid and the air, but those molecules will be taken out of the solution. So if you're exactly at the critical micelle concentration and you have some micelles, lots of monomers, a few micelles here and there, and you bubble air through or bubble oil through, then you're going to take monomers out of the system and you'll drop below the critical micelle concentration, which will cause the aggregates to break up and disappear. If you're way up here, however, and you bubble in some stuff, you're always going to have monomers in the system. Okay, last question. This was a problem that I gave in one of the practice tests, which gives two bubbles or droplets connected by a straw. And what this says, and this is in the problem methane gas in water, but this doesn't really matter what it is. Which side has the greater Laplace pressure? The smaller bubble has the greater Laplace pressure, and the air or gas or whatever is inside this will travel through the tube and to make this one bigger until this smaller one disappears, because even though the surface tension is the same, the Laplace pressure on the inside is bigger for the smaller bubble. So the question was, describe what happens as time progresses in terms of the following concepts: dipole self-energy, hydrogen bonding, surface tension, hydrophobicity, the Pauli exclusion principle, the van der Waals repulsive parameter B, Laplace pressure, and entropy. Use no more than 10 sentences or bullet points, and please underline the concepts as you write. So the point of this problem was to conceptually identify everything that's going on that's contributing to this phenomenon as it relates to using every concept that we learned in the course. So in the initial state, the bubbles are spherical to minimize the area to volume ratio with the hydrophobic solute. A hydrophobic effect is caused in the hydrophobic effect is what gives you an attractive force between hydrophobic solutes, or what causes hydrophobic objects to not dissolve in water, as these molecules are not dissolving in water. There would be a cage-like structure around a hydrophobic solute, which is caused by loss of entropy when water molecules at the interface adopt cage-like structures by hydrogen bonding in order to minimize their electrostatic or dipolar self-energy. As time progresses, the gas flows from the smaller bubble to the larger bubble. due to a difference in Laplace pressure created by a greater force per area of the small bubble, even though the surface tension is the same. The gas in the bubbles do not coalesce due to the greater entropy of the gaseous state. So why don't these, even though this pressure is very great, why don't the bubbles just squeeze in? You know, why is the gas driven from the left to the right? Why doesn't it just condense? Why doesn't this pressure, if it's so great, just condense it down to a liquid? The reason is because a gas exists because primarily of entropy, because of the domination of entropy. You get lots of entropic freedom by having a gas. And why do they repel ultimately from each other? That's because of the Pauli exclusion principle. And both entropy and quantum mechanical repulsion provide the basis of the van der Waals parameter B, which keep these things gaseous. So the point, you could have used these terms in any way you wanted, as long as they were correct. The point was just to look at this and describe everything happening on the basis of the intermolecular forces. So thank you very much for listening to this supplement and for providing your questions, and I will see you next time.